Good morning, all. Good morning. Am I audible? Am I audible and is the screen is visible? Okay. So once again, good morning all. This is the video lecture on design and analysis of algorithms. So we are into the last module, that is module 5, backtracking. So till now we have seen various types of algorithms. So first, divide and conquer, that is module 2. Module 3, greedy techniques. Module 4, dynamic programming. Module 5, backtracking. So in today's class, we shall go with a last type of algorithm type, that is backtracking. So in backtracking, we shall see what are all the concepts we are having. This is the outline of the module 5. So first you will be having backtracking. Second major concept, branch and bound. Third, knapsack problem. Fourth, complete and hard problems. Okay, so come for the backtracking. So in that we are going to discuss the subtopics that are listed below. So general method, Nqueens, subset, graph coloring, Hamiltonian cycle. So all these are the applications of backtracking. So after that, now we apply the backtracking for some of the applications like assignment problem, traveling salesman problem, and knapsack problem, and complete and hard problems. So come for the first one, general method. So what do you mean by backtrack? So can anybody can tell General meaning of backtrack. What is the general meaning of backtrack? So backtracking means I will tell you the entire concept in general method. So come for this backtracking, some problems can be solved by exhaustive search. Okay, so the problems can be solved by using exhaustive search. Backtracking is the more intelligent variation of this approach. The principal idea is to construct solutions one component at a time. Okay, so there are so many elements, some thing is to be done. So first is to construct the solution one component at a time and evaluate partially constructed candidates as follows. So you have constructed one solution for one component. There are so many components, okay, so that need to be solved. So now you are constructing the solution one component at a time and evaluate such partially constructed candidates as follows. So if partially constructed solution can be developed, continue. Okay, so so there are 10 problems. Okay, 10 components. So 10 components, you have to find the solution. So in that you take one component at a time. So if that one component can be developed, so continue for the second component, third component, fourth component, like that. If first component cannot be developed, okay, so then bad. If there is no option for the next component, that means, so if first component is completed, then it will go for the next component, that is second. If there is no option for next component means, so first component cannot be developed. At that time, we backtrack to replace the last component with its next option. So the method what you have taken, if it cannot be solved or developed, then we backtrack to replace the last component. Understanding? So that is the concept you are having. That means keep in your mind there are 10 components. So 10 components need to be solved. So in the but you are taking one component at a time. So taking one component at a time, we will go with a so finding the solution for one component at a time. So if the solution is found, we will continue. If the solution is not found, then we backtrack to replace the last component. That means first component with a next option. Okay. So now you come for the some concepts of backtracking. So first concept of backtracking is state space tree. So it represents the processing. Its root represents the initial state. The nodes of the first level represents the choices made. So nodes of the first level in the tree represent the choices made for first component of the solution. The nodes for the second level represent the choices for second component and so on. So node in a state space tree is said to be promising if it corresponds to is said to be promising means if it corresponds to partially constructed solution that may lead to complete solution. When you tell it as a promising, if partially constructed component solution for one component, so if we have created a partial solution, so if which may lead to complete solution, then we tell it as promising solution. Otherwise, it is called as a non-promising solution. Okay, so leaves represent either non-promising dead ends or complete solutions found by the algorithm. Okay, so in the majority of the cases, the state space tree for the backtracking algorithm is constructed in the manner of depth first search. If the algorithm reaches the complete solution, it either stops if just one solution is required or continues searching if for other possible solutions. Okay, so that is up to general method. So now after the general method, now you come for the application where you come across backtracking. So where you use the backtracking, so these are the applications we are using: Nqueens, sum of subset, graph coloring, Hamiltonian. Okay, so come for the Nqueens problem. So this is the Nqueens problem. So problem is to place n queens on a n cross n chessboard. So you have to place n queens. So 2 queens on a 2 cross 2. So you can take it as, if you are n, so it is 2 cross 2. If you want to place 2 queens on a 2 cross 2. So 2 cross 2 chessboard, so that no 2 queens attack each other by being in the same row or same column or same diagonal. So if n value is 2, you want to place 2 queens on a 2 cross 2 chessboard. So 2 cross 2 means you will be having 4, okay, such that no 2 queens should be in same row or same column or on same diagonal. So let us consider 4 queens problem and solve by using backtracking technique. So 4 queens problem. Since each of the 4 queens has to be placed in its own row, all we need to do is to assign a column for each queen on the board. So queen 1, row 1, queen 2, row 2, queen 3, row 3, queen 4, row 4. But the thing is, they should not be in the same row, they should not be in the same column, or they should not be in the diagonal. That is the condition. So n4 queens problem, initially it will be like this. The state space tree of this is shown below. It's shown below. So first queen is placed here. So you can see here, if it is placed in this row, this column, next it should not be placed in this row, this column, and this row. So at that time, now you can see, so this is the first one. Okay, so first one you have placed here. So come for second. So coming for second, you can't place it here, you can't place it here, you can't place it here. So where you will place? You can place either here or you can place either here. So you have 2 searches. So from this you can tell that you cannot place in here, or you cannot place in this diagonal. Either you can place it here or you can go for last column. So that's why we are given under 2, we have given here Q, under 3 here we have given here Q. Okay, so 1, 2, 3. So you can place either here or here. So this is for second Q. Second queen, you can place it in here or third or fourth place, because you can't place it in same column. First position you can't put, second position also you can't put because they comes diagonal. So you can put it in third position or you can put it in fourth position. So third position is represented here, fourth position is represented here. Okay, so using these two, you should put where you can. Understood? So that is 2, 3. Now you come here. So here for that, here you can see, can you place anywhere the third queen? So where if the second queen is placed here, so third queen can be placed here, because you can't place it in here, you can't place it here, you can't place it here. So you have to check. You can, for this particular row, for third, you can't place it in first position, you can't place it in last position, you can't place it in third position, you can place it in second position. So that's why you are given the second position here for third one. Okay, so now after that, after this, now you come for here. So this Q can be placed in second position also. If it is placed in second position, so you can't place a first position, second position, third position, you can place it in fourth position. So if it is placed in fourth position, now you see, so this column you won't get, So here also diagonal you won't get, here also column you won't get, here you can place it. So like that you have to keep on checking and you have to place. This is the solution. So first queen is at second, second queen at last, third queen at first, and fourth queen at third. So this is the four queens problem. Okay. This tree shows the expansion of nodes till it gets the solution. For multiple solution, it needs to be expanded further. Okay, so if other solution need to be found, the algorithm can simply resume its operation at leaf at which it stopped. Alternatively, we use board symmetry for this purpose. So finally, it should be pointed out that single solution for n queens problem for n greater than can be found in linear time. So this is the algorithm for n queens problem. So using backtracking prints all possible placements of n queues of n cross n chessboard so that they are non-attacking. For I equals 1 to n, if place of k comma I, if x of I is equal to x of k is equal to I, if k equals n, then write x 1 to n, else n queens k plus 1 comma n. So what the place will do? It returns true if the queue can be placed in kth row and ith column. Otherwise, it returns false. So X is the global array whose first k minus 1 values have been set. So that we can tell j equals 1 to k minus 1 if x of I is equal to I, or abs of x of j minus I is equal to abs of j minus k are in the same diagonal, then return false, return true. This is the algorithm for place. So that is the problem. So you have to write that particular thing. So have you understood? I hope you have got understood this particular concept. So now you come for the next upcoming topic. So we have gone with the n queens problem. So now you come for the sum of subset problems. So find the subset of given set A, A1 to AN of n positive integers whose sum is equal to given positive integer D. So you will be finding the subset. So you have to find the subset of the given set A equals A1 to AN of n positive integers whose sum is equal to given positive integer D. So example you come, subset you have given A is equal to 1, 2, 5, 6, 8 whose sum is equal to given positive integer D and D is equal to 8. There are two solutions. So 1, 2, 6 and this one we have taken it as 1, 8. So how you find D? So D is equal to of n positive integers whose sum is equal to given positive integer. D they have given it as 9. So how to find 9 from this particular situation? So you can take 8 plus 1 is equal to 9. Of course, some instances may have no solution. So it is convenient to sort the sets elements in increasing order. In the state space tree at node, if sum is not equal to D, we can terminate the node as non-promising if either of the following two inequalities holds. So S plus A of I plus 1 is greater than D. S plus, so this A of J can be taken as J equals I plus 1 to N, AJ less than D. Okay, so state space tree, we can take it like this. It starts with 0. So how you find the values? So they have given 1, 2, 5, 6, 8, D equals 9. So how you take this particular thing? So that is the formula we have taken. So understand carefully, find the subset of given set A of n positive integers whose sum is equal to given positive integer D. Okay, so for A equals 1, 2, 5, 6, 8 and D equals 9, there are two solutions. So how you find 9? Okay, so 1 you can take it as 1 plus 2 plus 6. So that will give you 9. Okay, so 6 plus 2 plus 1 is equal to 9, or you can also go with 1 comma 8. So is there any other solutions from the given subset? So you have to find the value 9 from this particular series. So if you take 5 plus 2 plus 1, 7, 8 you will get. 6 plus 2 plus 1 you will get 9. That's why I have written 1 comma 2 comma 6. Next one you have taken 1 plus 8. So 1 plus 8 is equal to 9. Okay, these are the two solutions here, sum of subset problem. So they will give you D value and A value. You have to find the set of solutions and also the space search tree. Okay. Of course, there are some instances may have no solution. So state space search, how you find. If sum is not equal to D, we can terminate as non-promising if either of the two inequalities holds. So that is S plus A of I plus 1 is greater than D. So S plus what is S? It is a sum. A of I plus 1, that is the array value, is greater than D. The sum is too large. So then S plus Aj less than D if sum is too small. So this is the state space tree you have written. Start with 0. So with 3, without 3. Which 3 it is? So we can take it like this. So with 3, without 3 it is 0. So next with 5, without 5. Here also with 5, without 5. So with 5 you can take it 3 plus 5 is equal to 8. Without 5 it is 3 only. So here also with 5, 0 plus 5, 5. Without 5, 0 minus, without means it remains same 0. So 8. So now with 6. So with 6 it comes 14. Without it goes 8. Okay. So with 7, without 7. With 7 goes to 15. Without 7 goes to 8. So 14. So 14 is, so now you have to comfort this condition. What is the D value? So D value they have taken it as 15. So 14 plus 7 is greater than 15. Yes. So now that's why you cancel. So if x is less than 15, no. So similarly you do for this cases. So using this formula, S plus A of I plus 1 is greater than D. The sum S is too large. So S plus summation J equals I plus 1 to N Aj is less than D. The sum S is too small. So this is up to sum of subset problems. Okay, so now you come for the next topic, graph coloring. So graph coloring. So this is the graph coloring what we have taken. So in this graph, how many edges are there? And anybody can tell how many vertices in the graph? Yes, answer in the chat box how many vertex you are having in the graph. Yes, in the graph you are having G. G is equal to V comma E. So G means graph, V means vertex, E means edges. So for this, how many vertex you are having? Yes, Kavana KP. Kavana KP. How many vertex we have in this graph? 10. See, we are having vertex number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you are having 10 vertices in this particular graph with edges. So edge 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so number of vertices is 10, number of edges is equal to vertices plus 1, that is equal to 11 vertices edges you are having. So come for the statement. So problem statement, given an undirected graph and a number m, determine if the graph can be colored with at most m colors. So if the graph can be colored with at most m colors such that no two adjacent vertices are colored with same color. So no two adjacent vertices should be colored with the same color. So problem is also called as colorability decision problem. So what's the thing? Determine the graph can be colored with at most m colors such that no two adjacent vertices are colored with same color. The problem is also called as colorability decision problem. So here the coloring of the graph means assignment of color to all vertices. So where you come across the applications to make the exam schedule for the university. So this problem can be represented as a graph where every vertex is the subject and edge between two vertices mean there is a common student. So every vertex is the subject, okay, and the edge between two vertices means there is a common student. So this is graph coloring problem where minimum number of time slots is equal to chromatic number of graph. So this is the graph coloring problem. Okay, so you have to tell where minimum number of time slots is equal to chromatic number of the graph. So come for the application. So first application we have seen mobile radio frequency assignment, where frequency are assigned to towers. Frequency assigned to all towers at same location must be different. Frequency are assigned to towers assigned to all towers at same location must be different. How to assign frequencies? What's the minimum number of frequency needed? This problem is also an instance of graph coloring where every tower represents vertex and edge between two towers represent there are in range of each other. So map coloring. So geographical maps where no two adjacent cannot be assigned to same color. 4 colors are sufficient to color any map. So this is the graph representation and its planar graph is represented here. So if the degree of the graph is D, it can be colored with D plus 1 colors. M colorability optimization finds the smallest integer m for which graph G can be colored. This integer is referred as a chromatic number, 3 colors sufficient for the given below. So next you come for the algorithm part, how to assign the coloring. So was formed using the recursive backtracking schema, is represented by using Boolean adjacency matrix. All assignments to the vertex such that adjacent are having distant integers are printed. So generate all legal assignments. Next value k. If x of k equals 0, return. If k equals n, then this is the algorithm what we have taken for coloring. So that is up to today's class. So remaining algorithm with a diagram state considering the state space search that we shall see in the next upcoming classes. Okay, so I hope you all have got understood this particular concept. So go through this module 5. So understand the concepts using the Google link. So I used to give my link as 1 dpmk So go through the link, kindly like, share, subscribe for the channel by using bell button preceded in the YouTube channel. Understand the concepts and learn the things. Okay, so I will be ending this particular session. So we shall see with the next class in the tomorrow's class. So thank you all. Stay home, stay safe.